Good afternoon, everyone. My name is Jordan, and I'm the manager of online education programs at COSI. Thank you all very much for joining us today for the 2020 COSI Science Festival. As you know, we have moved to an all-digital format, and we are glad that you're here with us today. I wanted to highlight one of the events that is happening all week and is coming to a conclusion today. That is the COSI Bio Blitz. In the Bio Blitz, you get to be a citizen scientist. We're asking you to go out into your neighborhood and take pictures of any wildlife that you may see and upload them to a website called iNaturalist. And from that website, scientists can use your data in their research. So it's very cool. It's happening today. If you want to get more information, you go to cosiscifest.org and you can find the BioBlitz listed there. And of course, we want to give a big shout out to all of our sponsors today, including our visionary sponsor, Battelle. Thank you all very much. We certainly could not have done this without you today. During the program, we will have the opportunity to take questions using our chat today. If you are on a desktop device, you can find the chat button in the center bottom of your Zoom window. If you're on a mobile device, you'll have to click over to a separate window, and then you can click back after you have entered your question or comment. It is now my pleasure to welcome you all to our program today with Dr. Lauren Babcock, and I will turn the program over to him. Thank you very much for joining us, Dr. Babcock.
Thank you, Jordan, and thank you all for joining today. I appreciate the opportunity to talk with you. And at the end, I'd be happy to take questions from anyone who has them. So what I'd like to do today is talk about some basics of gemstone and mineral identification, and I'm going to be using some basically fairly simple instruments, ones that I normally have at home, for example, and that some of you may have as well. If you don't have them, they're readily available. You can buy them online, and I'll give you some pointers as to how these things are used in mineral identification. So to start off, then let me share the screen with you. All right, I hope you all can see this. So what we'll do today is we'll go through some basics on mineral identification, and that will include gemstone identification. What I'm going to do is go through some basic properties of minerals. You may know many of these already. I'm going to perhaps give you some different ideas about some of the properties of minerals, including solids used as gemstones. And then give you some pointers on easy, effective tests for identifying pretty much any mineral you can think of. And as I said, most of these are tests that you can easily perform at home. Others that are ones that may require some instrumentation, but the instruments are pretty easy to come by and also fairly easy to use. Before we get into it too far, what I'd like to do is give you some definitions. And I would like to use, for the purposes of mineral and gem identification, a good practical definition of minerals. It differs a little bit from the International Mineralogical Association's formal definition of a mineral, but it's one that serves the purpose particularly of working with gemstones or things that we would regard as gem solids. And so I'm going to define a mineral as an element or chemical compound that is normally solid and formed by one of three processes, either geologic processes, that is to say igneous, metamorphic, or sedimentary activity, and I presume you all know what those things are. Through biomineralization, which means the synthesis of things like shells, bones, and teeth by living organisms, or alternatively, the synthesis of a mineral in the laboratory. In other words, the making of a solid that is chemically identical to that which occurs in nature, but which is produced by humans under laboratory conditions. All of these are things that I would regard as a mineral, and these are the sorts of things that we'll be talking about today. So let's talk a little bit more about some basics. Basically, minerals, as I've defined them here, come in two general forms, and these forms are crystals. Crystals are things that are solids that have clear, flat faces, or alternatively, they are amorphous or non-crystalline solids. And amorphous solids are ones that do not have flat faces. These would be things such as opal or volcanic glass, also known as obsidian. And let me switch over to the camera now and show you some examples of the two alternatives. Let me reduce the magnification here just a little. I assume you all can see this specimen here now. This is
Yep.
this is
Yes, we can.
Yes, you can. Okay, good, very good. This is my hand, obviously, moving the crystal around a little bit, and whoops, I'm going the wrong way here. Let's go this direction. Okay, and I think you can see this in this crystal. There are clear sides to it. I'm going to focus that a tiny bit more here. There we are. And here's 1, 2, 3, 4, 5, and 6 sides on this, for example. And as I turned the specimen, I think you could see a little flash of light off of each of the sides. That's how you know that that's an original crystal face. And there are also some little lines on it, little things that are striations, we call striations, that further indicate that this is a crystal. In top view, you can see very clearly this thing has 6 sides to it. This is a crystal of a mineral called corundum. The alternative is a specimen like this. I'm going to change the magnification again a little bit. This is an amorphous solid. This is obsidian or natural volcanic glass. And you can see that there is no evidence anywhere on the specimen of a flat side of any kind. What you see is just sort of broken edges all over the place and broken surfaces. And so that's an amorphous solid. And I would include both of those things in a definition of minerals. And I'll switch back to the PowerPoint now. All right, so the next question we ought to probably address is what is a gemstone? And this is a question that the people have varied definitions for, but the definition that I like best is this one. A gemstone can be defined as a material that is sufficiently attractive and durable to be used for personal adornment, or alternatively for some other art form. And under this definition, it's a solid that is beautiful, and that is what we regard as the key characteristic of a gemstone, is its beauty. And it doesn't really matter whether the stone comes from geologic sources, from biologic sources like bone, teeth, or shells, or is synthesized in a laboratory. Quite commonly, but not necessarily always, gemstones are cut and polished, or just polished, to enhance their beauty. And I know there's often discussion about the difference between a gemstone and a precious stone. in my view, there is no difference whatsoever. And so, I don't actually use the term precious stones, and I prefer the term gemstone for all solids that fall into this definition. Now, why I bring this up is because both of these things can be treated essentially the same in terms of testing procedures. We can test for gemstones, and we can test for minerals using essentially the same techniques. And basically what I'm going to show you here is how we can use some testing techniques to test mostly for polished stones of one sort or another, but we can use some of them also on unpolished stones. So what are the things you need to know in order to identify minerals, including gemstones? Basically, you need to know a variety of physical and optical properties. You need to be able to test for at least a number of these things. And some of the things that are normally tested for, or let me say that the things that we are ordinarily testing for are such things as the symmetry of the crystal, and sometimes also the shape within that symmetry group, or alternatively, whether the stone is of amorphous form. And I'll get to what crystal symmetry means in a short while here. We test for refractive index. We test for specific gravity or the relative weight of the stone. Color is the thing that usually people hone in on first, but as I'm going to show you, color is one of the least reliable ways of identifying a mineral, with a few exceptions, and should be one of those things that come in sort of last or pretty close to last in your testing procedure. We can test for fluorescence or change of color under ultraviolet light, for example. And we can test for luster, the appearance of light as it bounces off the stone. There are various tests for durability. These are the things that are normally used normally given as tests for minerals. In reality, although these techniques do work, in reality, when we have fine specimens, though, we generally don't want to use these durability tests because they tend to be destructive. We can use streak, another destructive kind of test, because that's actually the color of the mineral in powdered form. The way that a mineral breaks, that is to say its cleavage pattern or its fracture pattern, can be important in identification. If the stone will have, if it's a transparent stone, it will likely disperse light through it, and sometimes that dispersion leads to a quality we know as fire, or a rainbow effect, essentially, and that often leads to an identification. And then there are various things we refer to as phenomena, and I'll show you those in a short while, that are very helpful in mineral identification. There are a variety of other characteristics as well: magnetism, of course, or attraction to a magnet, conductivity of heat and electricity, things like this that are useful, especially for identifying or ruling out certain types of stones. And so I'm going to go through a couple of these examples here, some in more detail than others, and show you how we actually do tests of these sorts on the actual stones. And so the instruments that I'll be using in this demonstration are fairly simple ones. I'm going to use a magnifying lens, or actually what I'm technically going to use is a small magnifying lens called a loupe, a jeweler's loupe. As some may know this instrument under the term of hand lens. The one I'm using has attached an LED light and also an ultraviolet light source, and that turns out to be very handy. The UV light is extremely important in the identification of certain minerals. I will be using flashlights and a refractometer, and this is a fairly simple refractometer. It's a non-standard refractometer. It's a digital refractometer, easily obtainable online, for example, and for most purposes it's pretty good at narrowing down an identification of a stone. All right, so the next thing I want to talk about just briefly is the symmetry of crystals. Crystals form in six general patterns that we call systems. These systems are referred to as cubic, hexagonal, tetragonal, orthorhombic, monoclinic, and triclinic. And the system that the mineral forms in gives you some clue as to what the mineral identification happens to be. And so if you can identify what system the mineral forms in, you've gotten part of the way there. Now, in a cut and polished gemstone, for example, it may not be so obvious as to what crystal system this stone has formed in, but there is sort of an easy way to determine roughly what system the stone may have crystallized in. And let me just give you a quick example here. Perhaps the two most important of the crystal systems are the hexagonal system and the cubic system. A very large number of minerals crystallize in the hexagonal system. That is to say that when you view the crystal's edge on, as I showed you before with the corundum crystal, you can see very clearly 6 sides. And so some examples of minerals that crystallize in the hexagonal system are corundum, as I showed you already. In fact, what I showed you was an example of a sapphire, but rubies also crystallize that way. Beryl, including emerald and aquamarine, crystallizes in that way. And quartz, which is perhaps certainly one of the most abundant minerals at the surface of the earth, crystallizes in this system. The other sort of important crystal system is the cubic system. And in the cubic system, instead of having 6 sides like hexagonal crystals do, each of the directions on the crystal is essentially the same, or the distance from the center to any point at the exterior is the same as in any other direction. And examples of minerals that crystallize in the cubic system are things like diamond, garnet, gold, and silver. Now, why I bring this up and why I'm ignoring the others is going to be obvious in the next slide or two. I use the hexagonal system as just a proxy for all of the non-cubic minerals and non-amorphous minerals. And the cubic system is special because it differs from the hexagonal and other mineral systems. And the way that it differs is in something that we refer to as refractive index. Now, the refractive index is perhaps just about the most important term you need to know with respect to mineral identification. Refraction is defined as the bending of light as it passes from one substance into another. So for example, as light passes from air into a mineral, it bends. As the light beam passes from the mineral back out into the air again, it bends another time. And as it turns out, this bending is the result of air in minerals having different densities. So the amount of refraction or bending that occurs is a function of the density of the substance, in this case, the density of the mineral. And this is interesting because each mineral has its own density. And so what that means is that the degree to which light bends as it passes from air into the mineral is unique. And that unique bending amount is referred to as the mineral's refractive index. So in other words, the refractive index turns out to be essentially a fingerprint to the identification of a mineral. So measuring the refractive index is actually fairly simple and straightforward. And the reason I put up the cubic system and compared it to the hexagonal system is going to be more obvious to you now. The minerals that crystallize in the cubic system, because all the directions are equal within the crystal, it means that light passes with an equal speed through any direction in the mineral, in the crystal. Minerals that crystallize in the cubic system have only one refractive index, and we say that they are singly refractive. They have one refractive index. As it turns out, that's also true of amorphous minerals. Both cubic system minerals and amorphous minerals have one refractive index. They differ from all other minerals, that is to say, minerals that crystallize in all the other systems: hexagonal, orthorhombic, tetragonal, triclinic, etc. And all these other minerals have two refractive indices, and we say that they are doubly refractive. That turns out to be something really easy to identify in a mineral with fairly simple tools like a flashlight or a couple of flashlights. But let me get back to that in a moment. Each mineral has its own unique refractive index signature. And so, or in the case of the minerals that are doubly refractive, which is the vast majority of them, they have two unique refractive indices that can be used to identify them. Usually they're not too far apart. They're usually fairly close together. But the key here is that if you know the refractive index, you have a positive identification. It's the best way to identify a mineral, the best way to identify a gemstone. The way that we measure a refractive index is on a refractometer. And I'll show you what a refractometer looks like here in a short while. After you use the refractometer and you get a measurement on it, it's very easy to use lookup tables to identify the substance. And so let me just show you how this is done. Okay, now, Jordan, can you see the refractometer now?
Yes, I can. If you stop the screen share on your computer, we'll get a better view.
Okay, let me just do that. Better?
Yes.
Except for the refractometer, right? How's that?
Very good.
See the refractometer? This is a refractometer. I'm switching it on here. And you can see the numbers on it, perhaps?
Yes, we can.
Okay, very good. Okay, so I have a sample here that I'm going to test on the refractometer. This is a transparent stone. It's sort of a light purple color, and I don't know what it is, or I'm going to say I don't know what it is. And I'm just going to simply put this on the beam of light that will pass through the refractometer, and then hit the test button here. And oops, I'm getting a value that's a little too low. Just a minute. The thing needs to warm up again, it looks like. Oops, still getting a value low. Just a moment here. Unfortunately, this instrument is a little bit temperature sensitive. And I just calibrated it minutes ago. Okay, let's try it again. There, that's way off. Okay, let's give it another try. It should be hitting a number of 1.54, which is what I was getting before. Yeah, it's 1.48. Yeah. Okay, I'm going to probably need to recalibrate. But that's the technique that is used to identify the stone. And let me show you why this works. While I glue this thing on and let it warm up here on my for a little bit. I'm going to show you a couple of stones. under the other camera. And the first stone I'm going to show you is this one here. Let me set it on this. Yes, there we are. Can you all see that?
Yes, we can.
Centered on my dot. We're close to it. Okay. And let's focus. All right. And we magnify a little bit too. Okay. So the first thing I'm going to do is pull out a couple of flashlights here. And the first one I'm going to use is a standard LED, and I want you to see what the color of the stone looks like under the LED light from above. Now I'm going to turn to the side here, and I think you can see that what the color is from this direction. It differs from that at the top rather dramatically. Do you see that? We are looking at light passing through the stone down different axes. And so the color, the apparent color difference here is related to the different differences in the direction and the speed of light that light passes through those directions within the crystal. Okay, and so these two different colors here tell you that the crystal is doubly refractive. And so that means that whatever this thing is, it's neither cubic nor is it amorphous. And the second specimen I'm going to show you will obviously be the opposite condition. This is going to be a little harder to place. Let's go with that one though. Let me check the focus here a little. Okay, can you all see that? And again, is that clear enough? Okay.
Yes, that looks good.
Okay, good, thanks. The stone from the top looks about like this. It's sort of a slightly purplish red. And I'm going to do the same thing from another direction. And there's no change in the color. So what that means is that the stone is either from the cubic system or is amorphous. And that tells me how many refractive indices I should expect to find on this particular stone. Okay, now I'm going to switch back over to the refractometer. Can you see the refractometer now?
Yes, we can.
Okay, very good. I'm going to put that first stone on. So switch it back on. Oops. Value. I'll clear the memory here a second. And I'm going to put this one on. This stone is reading just a little low than earlier because it's just a bit cold, I think. So the values might be a little low. Let's see what this one comes up as. And it comes up as 1.65. I measured the stone earlier today. It was a little higher than that, getting a value around 1.72 earlier, and I can just go to a lookup table such as this one here, and can you see that? And just simply follow down, and as it turns out, at 1.7 or so, 1.76, this stone turns out to be corundum, and so it's a blue corundum, so that makes this stone a sapphire. We're going to test the other stone, and sapphire crystallizes in the hexagonal system, which means that it should have 2 refractive indices, and so we're so far all good in all directions. And I'm going to test this other stone. This one's testing on the, again, a little bit on the lowish side, I think. Earlier I got an index of about 1.7 on this one, and that puts us in the range for one of the garnet minerals, and that's what I've identified this thing as previously. And so garnet crystallizes in the cubic system, and so we're all good on that score as well. Now let's go back to the PowerPoint.
We've got a few quick questions. Can you spot a fake mineral by testing its refractive index?
A fake mineral. Let's see.
Maybe one that is being posed as something else.
Absolutely. I do that routinely. And actually, as long as the question is brought up, I can do that for you a little bit later. How's that sound? I can put on some natural materials, some synthetics, and also some imitations.
Thank you, Josiah, for that question. Another quick question maybe be from Caden. Can you tell us where we might be able to get a refractometer?
Yes, so this one I bought on eBay. It was, I can't remember how much this one is roughly $100 or something like that. Okay, other questions? Oh, okay. Okay, so what about minerals that don't have nice polished surfaces like these gem minerals do? How can you measure the RI? Generally, in order to use a refractometer, you need a really good clean face, usually a polished face, and typically the minerals need to be transparent or translucent, meaning that light passes through them easily or pretty well. If you don't have a refractometer to measure these smooth surfaces, you'll need to use other tests to narrow down a mineral identification. But as it turns out, these tests can also be used to confirm an ID made from a refractometer and the lookup tables. And so let's take a look at some of these other possibilities for testing. One is what we call specific gravity. And this is a fairly simple thing, although the words sound a little confusing perhaps. Specific gravity is simply the relative weight of a mineral, or the weight of a mineral compared to an equal volume of water. And you can actually measure specific gravity, but for most things, it's not really so necessary to do that. You can get a pretty good general idea of the specific gravity of two minerals by simply holding one in each hand, and comparing their weight. And I think everyone is familiar with how this works. I think everyone is aware that metals weigh much more than most other minerals, and so the specific gravity of the metals, like gold and silver and copper and so forth, it will be much greater than the specific gravity of, let's just say, quartz or diamond or something of this sort. But we can also use this specific gravity, or at least a relative weight of minerals, to compare some gem minerals. Like, for example, cubic zirconia, which is perhaps the most common simulant of diamond in use today in jewelry, weighs considerably more than an actual diamond. And so if you have two specimens, two cut specimens that are of equal dimension, that is to say that the same distance across and the same distance in height, and you hold one in one hand and the other in the other hand, you can close your eyes and identify the cubic zirconia. That is to say, you can identify the CZ, the cubic zirconia, by its relative weight compared to the diamond. You don't even need to open your eyes to identify a diamond under those circumstances. Okay, so it's a very simple test, and one that I use routinely for mineral ID. Color. Colors, as I said, it's the thing that probably most people use first to try and identify a mineral. And in fact, it's probably just about the most unreliable way of identifying most minerals. Most minerals come in a variety of colors. And let me demonstrate that. We demonstrate that by switching to the camera again. And let's see, let's go to the screen share. And so, anyone have an idea what this mineral is? Well, it's one mineral, and it's pretty much every color you can think of. These are all actual specimens, all collected from the same place, actually a stream bed in what is now Sri Lanka. And all of the specimens have a different color to them, it seems, or pretty close to all the specimens of a different color. This is all one mineral. And the mineral here is corundum. There are two varieties of corundum represented here. The red one is ruby, and ruby is defined as red corundum. And all the other ones, the blue, the green, the yellow, the white, the clear, the black, what am I missing here? I think there's an orange one in there, there's a purple one in there, and there may be others. All these other things are called sapphire. So sapphire is not, for example, just a blue mineral. It comes in a lot of colors. And in fact, blue is a relatively, it's in the minority in terms of the number of specimens of sapphire that are actually collected. And you can see that pretty clearly from this little collection of sapphires from Sri Lanka. The blue, there's really only one good blue stone in the entire mix. So if you were to use color to identify a stone here, you'd obviously come up wrong, except in the case of the one stone that happens to be ruby. I'm going to switch back again. Okay. Do you have the PowerPoint again?
Yes, we do.
Okay, very good. Okay. So color can be used, but I use it only sort of at the end of the identification process. There are some other things that can be used to identify minerals, and one of those fascinating things is what we call fluorescence. And fluorescence is luminescence, or sort of a color that is emitted by the mineral under the influence of ultraviolet radiation. And some minerals have a very distinctive kind of fluorescence. Now I'm going to show you a great example here in a moment of fluorescence in a mineral. I think I need to stop the screen share to do it. Is that right? Okay.
Yes.
Thanks. Okay, here we are. And now, can you all see this specimen? This is a specimen of a particularly nice sort of white to slightly pinkish mineral. And I'm going to use my loop here that has ultraviolet luminescence on it, or light on it. And you can see that this now luminesces a very different color under ultraviolet light. You all see that? It's a beautiful, slightly purplish or lavenderish kind of pink. Is that obvious on the screen?
Yes, it's coming through pretty well.
Okay, very good. And so that color is one of many that is possible for this particular mineral. This mineral happens to be calcite. And let's see, there was a question earlier about how we can spot fake minerals or imitations. I'm not going to show you an imitation this time, but I'm going to show you a synthetic. And this is an example of a synthetic stone. And let me just make sure I get it in the right place here. Yep, it's a little small. Let me show you both of these together then. Just to show you what this is definitely a synthetic. This is I think it's your right. This is a specimen of what is referred to as a boule. It is a manufactured or synthetic corundum, and it happens to be red, so it's ruby. And then on what should be your left is a cut crystal cut specimen from a boule just like this. And under ultraviolet luminescence, both of these change color. In fact, it's an amazing kind of color that I like to call day glow pink. It's totally diagnostic for a synthetic ruby. Do you all see that color change?
Yes, we can.
Okay, so that's what it looks like under normal LED light, and this is what it looks like under ultraviolet. A completely different kind of color, and that is that's a way of instantly identifying a synthetic ruby. Let's switch back here.
We had a question from Caden. Caden would like to know, do scientists still use color even though it's might not be the best tool?
Yes, we use color to a certain extent. I mean, some minerals are distinctive in terms of color. For example, gold or silver, platinum, they're pretty distinctive colors. And some minerals have fairly limited color ranges. Like, for example, tanzanite will be sort of blue to purple for the most part, even if it's light in color. But that's, most minerals crystallize, or most minerals have multiple colors, and so color is one of the last things you should be looking for to identify most minerals. There are clear exceptions, of course. Malachite, for example, is going to be green and black, and so there are definite exceptions. But for the most part, you want to wait until you've gone through other testing procedures to make the mineral identification, and then check to see if the color fits the rest of the information that you've obtained. All right. Next is in terms of characteristics is something we call luster. Luster is the appearance of light as it reflects off a mineral, and I'm just going to read through this because it's a little hard to show under the instruments I have here and with the video camera. But let me just kind of characterize these for you. Some classic examples of luster are what we refer to as vitreous luster or glassy luster, and you can think of this as what glass looks like. I think everyone knows what the appearance of light is, that when it reflects off of the surface of polished glass. That's what we refer to as glassy or vitreous luster. And this is unquestionably the most common type of luster in polished minerals. And it's also common to see glassy luster or vitreous luster on good crystal faces. So the luster sometimes is useful to identify things, especially if the luster is something other than vitreous. And some of the things that are not vitreous, for example, are what we call adamantine luster. And the word adamantine derives from both Greek and Latin words that refer to diamond. And so adamantine luster is diamond luster in effect. And believe it or not, a diamond is less shiny than glass. The surface, that is to say, when you see light reflecting off of the surface of a diamond, it will look less shiny than the light reflecting off of a polished piece of glass. And it actually looks kind of like if you took polished glass and then smeared some petroleum oil on it, or put some Vaseline on it. It looks like you've got maybe hand cream or something smeared on top of glass. That's roughly what adamantine luster looks like. And if your eye is sensitive enough and you learn to identify what adamantine luster looks like, it's pretty easy to identify a diamond by eye based on luster. Next is metallic luster. I think everyone is familiar with what the appearance of a polished metal is, and that's what we refer to as metallic luster. Another kind of luster is waxy, and that looks like the surface of a wax candle. It's almost as though it's a little sticky, for example. There are other kinds of lusters out there, but these are some fairly typical examples. Durability. Commonly, people are taught to identify minerals using durability tests. They do work to a certain extent. That is to say, they help to rule out certain types of minerals. But the downside of using durability tests, of course, is that they are destructive. And so if you've got a nice specimen, especially a cut and polished specimen, using these tests would be only a very last resort. But the kinds of tests that are used for durability are things like hardness, which is the resistance to scratching. And I think most people are familiar with Mohs scale of hardness, which organizes minerals from 1 to 10, 1 being the very softest, like talc, and 10 being the very hardest, like diamond. And things that have a higher number can scratch those with a lower number. So for example, number 9 on the hardness scale is corundum, 10 is diamond, diamond can scratch corundum. And number 7 on the scale, which is a very important one, is quartz. Both diamond and corundum scratch quartz. So that's one way of identifying a mineral. But for the most part, you don't want to try scratching your diamonds, or things you think are diamonds, nor your sapphires, which are corundum, nor even your quartz. And so it's not something we routinely use, except in sort of a last-ditch situation. Another durability factor is what we call tenacity, or sometimes it's called toughness, which is the resistance to breakage or the resistance to chipping and fracturing. Some minerals are extremely difficult to break, like jade, for example. The 2 kinds of jade are very difficult, very resistant to breakage, like chipping, fracturing, even hitting with a hammer. And interestingly, the tenacity of a mineral does not necessarily match well with the hardness. So for example, diamond is a very hard mineral. It has a hardness of 10, but it's not very tenacious. That is to say, it's very easy to break a diamond. It's very easy to chip a diamond, even though it's hard. It resists scratching well, but does not resist breakage well. And on the other hand, jade has high tenacity. It's hard to break it, but it is easy to scratch. It has a relatively low hardness. And so hardness and tenacity are quite different concepts. And then there are other kinds of durability factors that we characterize as stability. That is, for example, stability in relation to color change with respect to heat or ultraviolet radiation, for example, resistance to chemical dissolution, things like this. And in this regard, a couple of things are probably notable. In terms of color change in minerals, some minerals do change color through time, especially when exposed to heat or to ultraviolet radiation, for example, sunlight. And so amethyst, which is a mineral commonly used as a gemstone, for example, is poorly resistant to color loss in the face of ultraviolet radiation. And so amethyst that is left in the sunlight over a period of months to years will start to become more and more pale in color. And so that means it's poorly resistant to UV radiation. Some minerals like calcite and aragonite are easy to dissolve in the presence of acids like lemon juice, or even rainwater to a certain extent if the rainwater happens to be weakly acidic. And so these minerals are easy to dissolve. And so these are examples of durability factors. These are things you don't want to use for the most part with many of your specimens, unless you don't particularly care to lose a few bits and pieces. Another rather destructive test for minerals is what we call streak, and this is the color of a mineral powder. Often what is done is to take a piece of unglazed porcelain and rub the mineral across it, and that gives you a powder. This works with certain minerals, but as it turns out, most minerals form a white powder. So it does not work with the vast majority of minerals, or doesn't easily rule things out, that is. There are some exceptions, and these are the places where streak matter. And the exceptions are things like graphite, which is the stuff that is used for pencil leads. That has a very distinctive silvery gray streak, and that's why we have pencils made of graphite. Hematite, which is an iron ore, normally streaks reddish brown to black. Gold, as people probably know, streaks a brassy yellow. For a few of these types of minerals, streak is important in identification. Cleavage and fracture. This is something I think I'd like to show specimens of. Cleavage is the breakage of minerals along flat surfaces. And that's due to internal planes of weakness. And so the minerals simply break easily along these planes of weakness. The alternative to that is fracture, which is irregular breakage along surfaces. That is to say that the breakage occurs where there are not planes of weakness. And let me show you under the camera one more time the difference between these two things. On. Yes, we are. Okay. And let me back off the magnification a little bit here. Oops. Okay, this is an example of a feldspar form. This is actually called amazonite. And this is a specimen that obviously is broken. It's a crystal that's broken. And as I rotate it, you can see that there's a flat face here, and you can see light flashing off the surface, I think. That's a fracture plane. That's an internal plane of weakness. You can see in side view that there are a couple more of these internal planes of weakness showing up. If I tap this thing lightly with a hammer, which I'm not going to do, it would probably break along one of those cleavage planes. That's rather distinctive for a feldspar. The next piece I have here is an example of chalcedony. And this is a specimen that has just simply been broken. And broken in ways that do not reflect internal planes of weakness. And what you see instead is sort of shell-like shapes, sort of rounded fractures on this thing. And this is very distinctive for chalcedony and other forms of quartz. That's what this is, a form of quartz. and we refer to this as a conchoidal fracture. The word conchoidal comes from the Latin word conch, meaning shell. And so the breakage pattern on this specimen looks like little clam shells, for example. And that helps to narrow down the identification of the mineral. And as we come close to the end of the testing techniques here, I want to talk about a couple of things that I can show you, I hope, under the scope. And that is two sort of related concepts. The concept of dispersion, which is called the prism effect. And I think most people are familiar with that. When you pass light through glass, for example, the light separates into component colors, all the colors of the rainbow. And that's caused by the refraction that we talked about earlier. We know that, that violet light at one end of the visible spectrum bends more than red light. And so we actually measure dispersion as the difference between the refractive index, or the amount of bending of violet light, as compared to the refractive index, or the amount of bending of red light. And as it turns out, of course, each mineral has a distinctive dispersion value. So again, we have another sort of fingerprint, if you will, to the identity of a mineral. It's just that this one's not so easy to measure with simple instruments, that is. But we can actually get we can assess the relative amount of dispersion between two minerals pretty easily by looking at something that we call fire. And fire in a mineral is what we call is the word we use for rainbow-like flashes of light that are caused by dispersion. And let me show you an example of what this looks like. It's actually one of the things that makes diamond, so example, such an attractive sort of mineral is the stuff we refer to as fire. And let me just show you an example of dispersion or fire exhibited in a diamond, and then I'm going to show you in another mineral or two. Here. And I'm going to switch now to the camera. And what I'm showing you now is a specimen. Let's see if I can get the focus on it a little better. Maybe not. That's not particularly focused, is it? It's going to be hard for the camera. Whoa, okay. You're seeing the flashes of light here as I move this, I think. Okay, that's actually what I most wanted you to see. I'm going to enlarge it a little bit more just to make the flashes of light more obvious, because that's really the thing of interest here. And so now I'm going to move this thing around a little bit. Or maybe just bring the flashlight in, which would be perhaps even better. Okay, and now, when you see the flashes, and do you see colors? Some. Okay, the rainbow colors that I'm seeing here, which I'm not seeing so well on the camera, that's referred to as fire. But you can certainly see that there's a lot of refraction taking place within that stone. I'm going to put another one up and do the same thing. And I think you can see it again. And this time it actually looks like there's more of it. Can you see the refraction? See the fire? This one's actually more fiery than the stone I showed previously. The first stone was a diamond. The second stone was cubic zirconia. And that is to say that the cubic zirconia shows greater fire than a diamond. It's so much more, in fact, that it's generally easy to identify a cubic zirconia from a distance based on the amount of fire that it exhibits, and easy to differentiate it from a diamond based on the amount of fire.
We are almost out of time today, but I did want to get to some of the questions before we have to conclude.
Okay.
Let's see here. Earlier, we had a question from Marcy, and Marcy would like to know how you got interested in this field.
I'm not too sure. I guess I always was. My dad was a high school science teacher. I'm sure that was a major influence.
And Josiah has a question. Josiah would like to know, do crystals erode over time like other rocks?
Of course they do, yes. Okay. Well, I'm almost through the slide set here. Are there more questions?
Yes, we got one from Rebecca. Rebecca would like to know, what is the most rare mineral?
The most rare mineral. I'm not sure about that.
Okay, I'm going to look through for other questions if you want to continue with your slides.
Okay, sure. Let's do that. Okay, so other things that minerals may show are things we call phenomena, which are colors or moving patterns that happen when light interacts with the structure of the mineral. These are things like iridescence or a play of colors. There are various kinds of those. Pleochroism, which is color change under different lights, or like sunlight or LED light or incandescent light, or like what I showed you earlier, when light is directed along different crystal axes. When I showed you the color change that took place in the sapphire earlier, that was pleochroism. And pleochroism is distinctive, as I said before, for doubly refractive minerals. Some examples of iridescence are things like the cat's eye effect or chatoyancy. Some of you may have seen that before. Asterism is a moving star effect. Opalescence is a flashing rainbow of colors, which we see in precious opal, for example. Orient is the color change, the rainbow color change you see in shell and pearl, things like this. And then there are three things that appear in various kinds of feldspar minerals. They're called adulorescence, labradorescence, and aventurescence. Adulorescence is sort of a milky white to bluish, sort of billowy iridescence. Labradorescence makes the mineral look kind of shimmering like a metal, usually kind of dark colors. And aventurescence is little points of light that shine back at you because of little tiny inclusions within the mineral. And if we have time a little bit later, I'll show you some examples of these, but I think I'll just kind of finish up with one last slide here, and that is there are other characteristics that we can use to identify minerals. They include such things as magnetic susceptibility. I think everyone is aware that magnetite, for example, and some meteorites, the iron meteorites, can be attracted to a magnet. And then we sometimes use conductivity, heat or electrical conductivity, to identify certain types of minerals. And the idea here is that some minerals like gold and silver and copper are good conductors. That is to say, they permit the flow of heat and electricity through the minerals. But others like glass or cubic zirconia don't conduct heat or electricity very well, and they're called insulators. And we can actually use an instrument that called a diamond tester, or just a conductivity meter that tests for heat conductivity and electrical conductivity. And these are commonly used as diamond testers because the principle is that most diamonds, or at least more common kinds of diamonds, tend to conduct heat well, but electricity poorly. Whereas most of the simulants of diamonds don't conduct heat or electricity very well. There is one exception to that. So if you use a heat and electricity conductivity meter for a diamond, you will find that most diamonds will conduct heat well, but electricity poorly, and you can essentially rule out many of the imitations, or rule out a diamond depending on what the results are. There is a caveat here, though, and that is that there are a few diamonds that do in fact conduct heat and electricity well, and for these, a diamond tester will in fact yield a false negative. It will actually make the diamond appear as though it's synthetic moissanite, which does conduct heat and electricity well. Okay, and that's actually all the slides I wanted to get through. And I can take questions. I can show some other examples if you like.
Let's see, we had a question from Taylor. Taylor would like to know what is happening inside of a rock polisher?
Like a tumbler.
I believe that's what she means, yes.
Right, yeah, so you're rolling materials around with some grit, and so you're getting smaller particles rub against larger particles, and eventually just simply polishing things, almost as though it's very similar to what you do with sandpaper, for example. When you pass that over a surface, you start to smooth out the edges. You knock some of the bumps off the surfaces, and eventually you smooth the surface out with the interaction of the stones.
Right. Well, maybe we have time to see one more rock. Aaron has requested an aquamarine, if you have one of those that we can look at.
Sure. Okay, let me switch to the camera. Okay, here's a nice aquamarine. This one's from Brazil. And it's a nice sort of pale blue color, pale bluish green color actually. It's doubly refractive because this is actually the mineral beryl, and it crystallizes in the hexagonal system. So actually, it'll have different colors as you view the light in different directions. Kind of subtle in this example.
Excellent. Well, thank you so much for showing us all those samples, Dr. Babcock.
You're welcome. Thanks for joining us.
Yeah, I'd like to thank all of our guests for their great questions and for their request to see these different samples with us. And we hope you enjoyed our program today. Again, our Bio Blitz is happening the rest of this weekend. So if you are interested in citizen science, we suggest that you go to the COSI website, cosiscifest.org, to look up the details of that, and you can go out into your neighborhood and help us with some citizen science. If you do, we want to see those pictures. Be sure to use the hashtag COSISciFest so that we can see what you're doing out there with our Bio Blitz. Thank you all very much for joining us today. We hope to see you in our programs this afternoon. Have a great day.